So, yes, it is word problem day. All right, so, example number 1. Mrs. Hoff searches the couches in her home for loose change and collects it. 1 year, she collected $207. Okay? She put this money into an account for a rainy day that pays 4% interest that is compounded monthly. Question part A. Write a model to represent the money in her account. Okay? When we're talking about compounding something, we have a very specific model that we're talking about. And that is A equals P times 1 plus R divided by T to the, not R divided by T, R divided by N to the NT power. Okay. That's the formula that gets used for compounding, non-continuous. For continuous compounding, that's PERT. Okay. That's A equals P times E to the RT power. Okay. So, there's 5 things to identify. First, A is the amount in the account. Okay, that's your ending amount. How much you have right now. P is your starting amount. How much you put in to open the account, or how many organisms you had at the start of your experiment. 1 is 1. R is the rate. Now, the rate is probably going to be given to you in terms of a percentage. The downfall with that is we need to use it as a decimal in the problem. So we have to convert a percentage to a decimal by moving the decimal point 2 spots to the left. Okay? So whatever the decimal or wherever the decimal is, we move it 2 spots to the left. Bless you, by the way.
Thank you.
You're welcome. Okay. N is the number of times compounded. And that usually is per year. Okay? So if we are compounding monthly, okay, that means we would compound 12 times. If we are compounding weekly, that would be 52 times. If we're compounding daily, 365 times. Okay. T is the time, and the time is in years. So if we're asking for 1 year down the road, how much money's in the account, your T would be 1. If I'm asking for 17 years down the road, T would be 17. If I'm asking for 18 months from now, T would be 1.5. Okay, because 18 months is 1.5 years. Okay. So, that is the explanation then of what the formula that we're going to use. So, A is the amount that's going to be in the account at any given point in time. P is how much money she started with. How much money did she start with? $207. 1 is 1. R is our interest rate. What is our interest rate?
1.2.
No. is what? It's just 0.04. Yep. Because the one part is right here. Okay, it's right there already. So it's just 0.04. N is the number of times that we're compounding. How many times are we compounding this one? 12, because it's monthly. To the 12, because that's our N again, T power. Okay. B says, how much money will be in the account after 5 years, assuming that, since this was her rainy day fund, assuming that it didn't rain. Okay, meaning she didn't take any money out of the account, left it all in there. So then A would equal 207 times 1 plus 0.04 divided by 12 to the 12 times 5 exponent. Okay? So figure that out for me on your calculators. FYI, for Thursday's test, you will need to have yourself a calculator. We know what you get when you get it. What you got, Boo? Too much. Yeah. What are we talking here? Talking money, right? So would 0.7 work?
Okay. $252.74.
74 cents?
75 cents.
75 cents. I like $252.75. Okay. Really, I get 252.746294945, but because we're talking money here, we will round to the nearest cent. Okay? If we were talking people, we would round to the nearest person, to the nearest whole number. It's whatever we're talking about in terms of that. If you can have decimals, we'll give decimals. If it's money, we'll have decimals, but we'll go out to 2 places. Okay? If it's people or objects, then we can't have partials of, then we'll go to whole numbers. Okay? Part C, how much money is in the account after 15 years? Figure that one out for me. While you're figuring that out, can I just take my previous answer, because that was 5 years, can I just take my previous answer and multiply it by 3? Can I do that? No, because interest grows on itself, and so it's an exponential function, so it's going to keep growing, yes, at the same percentage, but that percentage will grow as time goes on. I get $376.80. Yes? Or what you can do, Kate, is you can start on the inside. So start by going 0.04 divided by 12 equals plus 1 equals to the 60th, or not 60th power, to the, what is that, 180th power equals times 207. Okay. You can always start in and work your way up. Okay? All right, what I'd like you to do now is I'd like you to try the Stanke unit problem. Okay? The amount of toxic fumes measured in Stanke units, or SUs, left in the family truckster after the road trip to Florida can be modeled by f of h equals 2,000 times 0.87 to the h power, where h is the number of hours after we got home. Question A, how many fumes were in the van when we got home? Question B, how many fumes are in the van 24 hours after we get home? When I get home, how long have I been home? How many hours have I been home when I get home? 0 hours. So h here is equal to 0. Okay? So f of 0 is 2,000 times 0.87 to the 0 power. 0.87 to the 0 power is equal to 1. 1 times 2,000 says that when we get home, there are 2,000 Stanke units in the family truckster. Okay? 24 hours later, there are now, so now this is my H. So F of 24 is equal to 2,000 times 0.87 to the 24th power. 2,000 times 0.87 raised to the 24th power gets me 70.712 Stanke units of fumes in the van. Okay. We'll come back to those two problems momentarily. Okay. Question number 3 says, when a plant or animal dies, it stops acquiring carbon-14 from the atmosphere. Carbon-14 decays over time with a half-life of about 5,730 years. So that means that if we had 1 gram of carbon-14, 5,730 years later, we'd have 0.5 grams of carbon-14. 5,730 years after that, we would have 0.25 grams of carbon-14. 5,730 years after that, we have 12.5 grams of carbon. Always decaying in half. Okay? My question to you is, if we're always decaying in half, can I ever get 0 grams of carbon-14 left? Or 0 units of carbon-14 left? small it gets, there will always be some left in there. Okay? So no, so I can't get 0. So 0 is out of the equation when we're dealing with carbon dating. Okay? The percent P of the original amount of carbon-14 that remains in the sample after T years is given by the equation P equals 100 times 1/2 to the T over 5,730 power. Okay? What percent of the original carbon-14 remains in the sample after 2,000 years? Well, 2,000 here, is that a T or is that a P? T or P? My only two variables in this problem. That's a T, that's a time. Okay? So then we're going to go P here is equal to 100 times 1/2 to the 2,000 over 5,730 power. What percentage do we have left? Percentage, anyone?
78.51.
78.511 if we rounded it to 3 decimal places? Okay. That's what we've been kind of doing in the last couple of worksheets, so let's keep in that mode. Yep. Unless it's a problem where it was like person. You know? Yeah. Okay. Now, logically, does this make sense? 2,000 years from now, we've got 78% of our carbon-14 left. Logically, does that make sense? If I were estimating, would 78% be a good estimation? Why, Bill?
Because it takes 5,730 to take away half of it.
Okay.
So you just take half.
Because 2,000 is about half of that, right? So 50% in that 5,000, half of it would be like 25%. So we should be somewhere around 75%. Okay? Yeah? That's the logic that I would go under. Yeah, we should be somewhere around 75%. And we are. So logically, it makes sense. Part B. What percent of the original carbon-14 is in the sample after 20,000 years now? So now my T is 20,000 years. And what do we get? What do we get for a percentage left of carbon-14 after 20,000? 8 point what?
I just rounded.
Round to 3.
3?
Yeah. So 8.898. Agree? Logically, does that make sense? Okay. So 5,730 years after this organism stopped living, how much should be left? What percentage should be left in 5,730 years? 50% should be left, right? And then another 5,730 years, or 11,460 years later, how much is left? In 2 half-lives, how much is left? 25%. Another 5,730 years later, or 17,190 years, how much is left? 3 half-lives. How much should be left after 3,000 or three half-lives, or 17,190 years? First half-life gets me to 50. Second half-life gets me to 25. Third half-life gets me to 12.5%. Okay? So 17,190 years later, we should be at 12.5%. Okay? Another 5,730 years would put me at 6.25%. And so that 20,000 is halfway in between that third and fourth half-life. Okay? Now, let's take this in another direction. Let's go with this question. This question is, when will the sample have 1% of the original carbon-14? Now, instead of being given a T value, I have a P value. So I want to know when there's going to be 1% left. So 1 is equal to 100 times 1/2 to the T over 5,730. How am I going to solve that one? No, because it told me that P was in percent already. How am I going to solve this one?
Don't you divide by 100?
Love it. Divide by 100 first. Isolate the log. Or, excuse me, isolate the exponential in this case. That gives me 1 over 100 equals 1/2 to the T over 5730 power. Now what? Do we have our exponented term isolated? No, can't. It's in the exponent. What? Nope. Base is being controlled by something. What do you gotta do? Switch to what? To logarithmic form, because my exponential term is isolated. Okay. So, what is my switch going to be? Log base 1/2 of is equal to So we could figure out what log base 1/2 of 1 over 100 is. Okay. I get 6.643, right? And then what am I going to have to do with that? What am I going to do with that then? Multiply it by 5,730, And I get that T is approximately 38,069.296 years.
How do you take the log into the calculator?
You gotta use change of base. So you do log of, or log or natural log of 1 over 100. Close your parentheses. Divided by log or natural log, whichever one you use, got to use the same one, of 1/2.
Why do you put the other one, or the 100 one first?
Because that's a change of base formula. You take this log of this one divided by log of your base.
Okay. So you can just turn this one back forward. Like it doesn't actually matter.
Yes, it matters. Okay. Now, bonus question. Let's go back a slide. So we're in Stanky units here now. You tell me when there will be 500 Stanky units left in the van. Okay? So question C is, when will there be 500 Stanky units left in the van? I get 9.955 hours. Yes? Okay. We can go back one more problem. And we can say when this is now going to be D. When will she have enough money to buy a $500? What do you want to buy? What does she want to buy? $500. A phone? Okay. So when will she have $500 in her account to buy herself a cool phone? So I get T is 22.084 years. Is what I got. Okay. Money really doesn't grow very fast in an account when you're only compounding it monthly. Okay. It'd be even slower if we were compounding yearly. Which is why most banks compound daily. Okay? So, no formative tomorrow. I have a salmon colored worksheet here for you for Wednesday. Wednesday we will review. Thursday we will take a test.
Can I turn in my corrections for the two assignments Wednesday?
Sure.